Okay. Do-do-do. All right. Hello, everyone, and welcome back. Let's go ahead and record. Try that again.
Recording in progress.
Hello, everyone, and welcome back. We are continuing on with our course. This is let's get into the pencil feature. Here we go. This is the MCT4C. We are in Unit 3, and this is lesson number 14 of the course. Technically, I think this is class 23, but lesson 14. And today we're going to be looking at the addition of vectors. And so in general, the concepts we're going to be looking at today will be the triangle law of vectors, the zero vector, the parallelogram law of vectors, as well as a generic vector addition. And for the vector addition, we're going to be looking at vector diagrams, similar to what we did on the lesson of last time, as well as just general sketchings. Okay, so we will know things went well when we'll be able to add vectors by placing them either head to tail or tail to tail and apply the triangle or parallelogram law of vectors. It sounds to be some sort of like grandiose concept, but it's actually quite logical. Okay, so all we need in order to continue is we want to be able to sketch a given vector. So as a point of review, we're going to sketch a force of 500 newtons on a true bearing of 245. And so recall, a true bearing meant that when we draw a Cartesian plane, we label north, and we go around from a clockwise direction. Now, in this case, 245 degrees is equal to 90 plus 90 plus 65. And so that's going to end up in quadrant 3. And so our vector will be down here. This angle in here ends up being 65 degrees. And that force is going to be 500 newtons. So this is a sketch of what this would look like. Today, I don't need we don't have the Desmos calculator or the graphing calculator. We just don't need them. And we're good to continue. Okay, so let's consider the following vectors. And so these are vectors just taken from the book, but again, these are just, you can use any two vectors for this. But we have two given vectors, vector A and vector B, and we're interested in the addition of this. So what does this look like? And so if you see on the right here, we have sketched out what vector A looks like. There's vector A, and here is vector B. And note that these two vectors, these are just random vectors from the textbook, but they could be really anything you'd like. The more interesting ones are ones like this, but they could be something called collinear, but that's a topic for another day. So how might we add these together? Well, it seems to be that, suppose we start with, say, vector A, like this. So we seem to have some sort of initial starting point, and we move off towards the northwestern direction, and then vector B has us move towards the northeastern direction. And so perhaps it might make sense to draw out our vectors as such. And so we move in the direction of A, pause, and then move in the direction of B. And then afterwards, the resulting vector will be the sum of the desired vectors. So this will be vector A plus vector B. So here, sometimes we call this the resultant vector, where this is the solution that we were looking for. This method is what we call the triangle law. Okay, so we start at an initial point, we apply one vector, and then we can apply the other vector. Now, by a similar token, could we have, say, started with vector B? We sure could have. So using the same diagram, I could have moved in the direction of B, and then afterwards moved in the direction of A. And if you notice, we end up with the exact same resultant vector, A plus B. So the first triangle we did was the triangle law of vectors. This is the second one. This is actually called the parallelogram, or the parallelogram law of vectors, where we go ahead and actually sketch both sets of these, because we actually end up forming, get this, a parallelogram. So again, the triangle law of vectors is where we drew one vector, say vector A, and then we drew the other vector, vector B, and then we connect the tail of A to the head of B, and we call this vector A plus B. So that's the triangle law. The parallelogram law of vectors is where we create two sets of those. And I have notes here coming up that'll help describe this more in detail, but I wanted you to get an intuition for how we would describe these. Okay, and then the resultant vector we call is the A plus B. Resultant sounds like a fancy word, but remember it has as part of its root, think of it as the resulting vector, and just resultant is a better tense to describe this. Okay, and again, the only thing I have to mention that these are not to scale. If I was on a computer, I would just drag these using my mouse, but I'm on a Galaxy Pad right now, so it doesn't quite look that way. Okay, let's continue on. So the triangle law of vector addition runs as such. So we already described it above, but now we're going to describe this in words. So we're going to let A and B be any two vectors arranged head to tail. The sum A plus B is the vector from the tail of A to the head of B. Okay? And so here I have two easy vectors for us to consider. Easy is in quotation marks. These are what we call perpendicular vectors, A and B. And so here, the point of this question is that we want to illustrate that vector A plus B will give you the same resulting answer as vector B plus A. And so here, these two vectors happen to be perpendicular. For the purposes of our answers, is there anything fancy about them being perpendicular vectors? No, not at this juncture. The reason why we like using perpendicular vectors is because it's easier to illustrate what it should look like. Whereas if we had to look at the above question, like I had to try to estimate the best way to kind of sketch these, and my diagram might be slightly off. Whereas if they're perpendicular, very easy to show the point I want to get across. Okay, so here we start with vector A. So there it is here. And if I add on vector B, I just put that as I put the tail of B at the head of A. And so I have the resulting vector, A plus B. And if I were to draw vector B first, there it is here, then I could add on A. And then we still get the exact same vector, A plus B. So the order of the vectors does not matter. And keep in mind that with respect to two vectors, this also extends to three or more vectors as well. Okay, it's just that we show this using two vectors because it's easier. And if you want an intuition for how this could work, you could imagine, say, an additional vector, say vector C, that's another horizontal arrow, can be done the same way. And I leave that to you as an exercise to kind of sketch that that's going to be the case. Okay, let's continue on. Okay, so we're going to prove that vector A plus B is the same thing as vector B plus A. And so we can see here by this diagram is going to help us prove this is the case. And so all he did here was combine our two images together to give this resulting image here below. So again, for the purposes of color coding, let's call vector B, put that in green, vector A, we'll put that in red. And so the resulting vector A, it will be the vertical component here. Perhaps I should color this over in red. And vector B will be the horizontal component. Okay. The resulting vector is A plus B, which is going to be the diagonal. And again, you can show this with non-perpendicular vectors. It's just easier to show it with perpendicular vectors. Okay, so you can see here that regardless of whether we start with A or B or B and A, they both still have the initial starting coordinate or starting point, say here. And if we move in the direction of A, then B, you can see that's clearly equivalent to the direction of B, then A. So the way to prove this one is to sketch a vector diagram to verify. Now, we can prove this. We're not going to get into proofs because we can use numerical values to help prove this. But for our purposes, this is enough to show that this is the case because of the diagram helps illustrate this point. Okay, let's continue on. And so here, when we want to add more than two vectors together, you can do this. So to add 3 or more vectors, place them head to tail so that the tail of the second vector is at the head of the first, the tail of the third vector is at the head of the second, and so forth. And you just kind of keep going. And so the sum is the tail of the first vector and the head of the last vector. So here, if I'm interested in finding the sum of A plus B plus C plus D, so if you notice here, here's vector A, here's vector B, here's vector C, and here's vector D. Your intuition should be telling you that if I want to find out the resulting vector, it seems as if the answer to this is just going to be vector AE, right? And so this is another kind of way to help visually show what this looks like. But you can see based on the diagram that we had here that if I want to add all of these vectors together, these are given by, say, vector AE. Now, it's worth noting that here we have vectors A, B, C, and D, which is just like the name of each of these vectors. But based on this diagram, we can also illustrate this using the point and head method. So what I mean by this is we can say that vector A is equal to, can see vector AB. Vector B is going to be equal to vector BC. Vector C would be equal to vector CD. And vector D, you could see is equal to vector DE. And so the nice benefit about the way we're sketching these is that you can see that the vector, if you have, say, for example, vector A is equal to vector AB, we start at the tail, we start at A and end at B. So the notation of these is necessary. And so if we wanted to describe this geometrically, this geometric solution algebraically, it can be done as below. So we took the summarized notion from above. So we said that vector A plus vector B plus vector C plus vector D is equivalent to vector AB plus BC plus CD plus DE. So this was what we analyzed from before and said, oh, okay, well, all we're going to do is instead of writing these out as single points, since we have a diagram, we'll just use 2 letters to help encapsulate that data better. And then we're going to make some observations. So if you notice here, our first vector, if we have a look at AB plus BC. So here, AB is this vector, and BC is this vector. So what's a vector that's equivalent to AB plus BC? You can see that the equivalent vector would be AC, which is below. And so we're going to transform this vector AB plus BC into vector AC. Similarly now, I can also then state, what if I take vector AC and I add on vector CD? Well, this is vector AC. Here is vector CD, and we can see the resulting expression will be vector AD. And so I can replace this vector AC plus CD with vector AD. And by a similar token here, if I were to take vector AD and plus vector DE, we can see that that's actually the same thing as just vector AE. Okay? And so a nice little shortcut for this, you might have noticed, is that if you arrange your vectors like this, say, for example, AB plus BC plus CD plus DE, you get like a nice little link between these where A ends up B, but then B, the next vector starts with a B, then BC ends with C, then the next vector begins with C. And so if you have this nice little pattern here where the beginning of one vector is the end of another vector and you're explicit, the solution to this will just be the beginning of the first vector and the end of the last vector. So you can just call this vector AE instead. That wasn't so easy to deduce right from the start because here we had vectors A plus B plus C plus D, and we had to go ahead and interpret this diagram to understand kind of roughly what was going on here and what we were doing. But we were able to, you can actually, again, if you use two letters to represent the vector, we actually have a nice little conclusion that we can draw from this. This ends up being an extremely important technique with respect to the addition of vectors. Okay. We have a consequence here. So we have something called the zero vector. So the zero vector, which we denote with just a zero with an arrow on it, has zero length and no specific direction. The sum of any vector and its opposite vector is the zero vector. So suppose I take vector A plus the negative version of A, vector A, we get vector 0. So to be clear, suppose this was vector A, and this vector was negative vector A. So it's the exact same vector, same magnitude, but it has opposite direction. Okay? When we add those 2 points together, essentially what happens is, or those two vectors, we move along in one direction, and then we go back to the initial starting point. So in essence, we didn't really get anywhere. And so the consequence of this is that the zero vector has no length, and it just has no given direction. It has a lot of analogs with the number 0, whereas 0 is neither positive or negative. It just uses a placeholder. So the zero vector, vector 0, is defined to be a vector so that the sum of any two vectors is always a vector. Okay? Because otherwise we'd have a problem here where if we tried to add two vectors together, we could end up with a scalar. But that's not the case because we're going to define 0 as a vector. And so we make the stipulation, and so I said analog, not the same as, vector 0 is different than the number 0, although they do have similar things, similar properties. Okay? So with this, there's a little bit of a consequence from this. So just as is the case with when we're adding together numbers, using, say, the commutative associate and the identity property, there are vector equivalents for this. And so if we take vector u plus vector v, that's the same thing as v plus v plus u. And so remember, the analog was the numbers, and all we're saying for this is that if you have 3 plus 5, that's the same thing as 5 plus 3. The associative property of vectors says that if you take the sum of u plus v, and then add w, that's the same thing as u plus the sum of v plus w. And so the equivalent for that would be, say, if you took 2 plus 3 and added 6, that's going to be the same thing as 2 plus the sum of 3 plus 6. So the order that you add things is irrelevant. You can also notice that you could have arrived at that conclusion from here. So for example, you could have added, say, vector BC plus CD first, and you would have had vector BD. And then if you were to add AB plus BD, you get AD. So you get the same kind of result when you work around with this. And similarly, if you take vector V plus vector 0, that's just vector V, or if you prefer, the vector 0 plus V. So all we're saying here is if you take 1 plus 0, that's just 1, but it's also the same thing as 0 plus 1. So adding 0 doesn't change the value of something. And again, this might not seem to be particularly useful right now, but the relevance of this is that, we can go ahead and prove some properties using the fact that when we add 0 to something, it does not change the value of it, the 0 vector to something. Okay, so we're gonna have a look at some vector addition. And so note that these are going to be our vector diagrams. And in this course, we do a lot of these. And so just become comfortable with them. And so in parallelogram, A, B, C, D. So remember, a parallelogram is a quadrilateral in which AB is parallel to DC, DA is parallel to CB. Excuse me, just a moment. Oh, sorry, excuse me. And so we note that we have two sets of parallel lines. E will be the intersection of diagonals AC and DB. And so we're going to name a equivalent vector to each expression. So, and I just redrew the same diagram twice, so that way we can write on this and kind of color code this as best we can, because I only have 3 colors, and so I'm going to draw all this. Okay, so what's the equivalent to vector BD plus DA? So based on that rule I told you from earlier, you'd think the answer should be BA, right? Because we can see that the vector, we have BD then DA, so it seems like the answer should be just BA. So let's go confirm if that's the case or not. So vector BD would be this one, and then vector DA would be this one. And so you can see that the vectors are lined up head to tail, or tail to head, and so forth. And so the resulting expression would be going from B over to A, which is what we wanted to show. What about vector AB plus BC plus CD? Again, our intuition says that since these match up, our answer should be just vector AD. So let's go ahead and show this is the case. So here, if we take vector AB plus vector BC plus vector CD, then that means what really happened is we started at A and then ended up at D. So this would be the resultant vector that we're interested in, which is the case. Okay. Similarly, what about vector AD plus DB plus BC? Again, our intuition tells us that the answer to this should be vector AC. So let's confirm this is the case. So vector AD would be this one. Vector DB would be this one. And vector BC would be this one. And so what really ended up happening is that we traveled the distance from A to C, which seems intuitive. So that means we know that this is going to be correct. So the vector diagrams aren't always going to be lined up so nicely. So for example, if I wanted to add, say, vector BC plus DB, we notice here that these values are not similar. Namely, we end at vector C and begin at vector D, so we can't just assume the answer is vector BB, which we're not sure what that means yet, but let's have a look. Okay, so vector BC. So that means we start at B and we go to C. The next vector we have is vector DB. So that means we start at D and we go to B. And so the reason why we have these diagrams here is because this is a nice way to help us interpret what we're looking at. So here, when we started off with vector BC and then we came from vector DB, this appears to be pretty similar to our answer. It seems to be the case that this will be our solution, will be vector DC. So how does that make sense? Well, we're actually going to use the commutative property of vectors, meaning that if we have vector BC plus DB, that seems to be the same thing as vector DB plus vector BC. And then you can see we end at vector B, begin at vector B. So that means we've got vector DC, which is what we were looking for. Similarly, if we have vector FH, there's no vector FH here, but we'll just try this one as a side note here. For our purposes, let's go with vector AB plus vector BA. I'll have to change this in my notes. I'm not sure why I put FH there. But let's go with vector AB plus vector BA. Okay, so here what this means is that we go from A to B, and then from B back to A. Okay, so we go from A to B, and then we go from B back to A. So the solution to this seems to be just 0, right? We ended up where we started. And if we were to take vector FH plus HF, the answer to that would also be vector 0. Even though we don't know what those vectors would look like, this is just saying we start at some given point and move in a direction, and then we want to add on the opposite of that. So hence we ran into the opposite vector. So we can conclude then that this is going to be the 0 vector. Okay. We have vector addition practice. So we have more examples of this in action. So at this point, this would be a good time for you to go ahead and pause the video and try this out for yourself. Okay. So let's see what we've got. So this is vector addition practice. So the diagram below shows a rectangular prism. So instead of a parallelogram, just a rectangular prism. So we just took a rectangular prism, just labeled the 8 corners, A, B, C, D, E, F, G, H. And we're going to determine a single vector equal to each of these given sums. Okay, so for the first one here, we have vector AE plus vector HC. So we already noticed that these don't appear to have any similarities, so we should sketch to see what they look like. So vector AE, so we start at vector A, end at E, and then we have vector HC. Oh. Trying to connect lines in a rectangular prism apparently is quite difficult. There it is here. And so we can see, these don't appear to, they don't really match up head to tail. But we can recall the fact from the past that vector HC has an equivalent vector that is going to be convenient for us. So note that vector HC is equal to vector EB. And so we can rewrite vector AE plus HC as being vector AE plus vector EB. And you can see then the resulting vector will be vector just AB. And again, we saw we have a vector that ends at E and begins at E. So we know that the resulting vector would be just the start of the first and the end of the last. Okay. For letter B, we've got vector AD plus AE plus AB. Okay, fair enough. So we're starting at A. So we have vector AD. Here it is here. Then we have vector AE. There it is here. And then we have vector AB. And so where do we want to end up here? And so again, the way to think about this is just to think about the fact that where could we position these vectors that might make more sense perhaps. And already you might be thinking of the parallelogram law, because you might be thinking, well, if I were to connect those two vectors, it seems as if I'm interested in the resolution of vector A to F and then tack on an AD, and that would be correct. So that's one way to think about this. So here, going from if you take vector AD, AE, and AB, it seems like we're going from one corner of the prism to another corner. And so there it is here. So you could say that this is the same thing as vector AG. Now, another way to think about this is if you want to instead, like you want to apply the same kind of logic that we did from above, vector AD looks okay. And then we could add on, say, vector DC, and then add on vector CG. So we can make a stipulation and say that vector perhaps I'll write it off to the side here. So we could say that vector AE is equal to vector DH. And then we could say vector AB is equal to vector HG. And the reason why I chose those specific vectors is because if I reformulate this, this becomes vector AD plus, instead of vector AE, we'll write DH. And instead of vector AB, we'll write vector HG. And so you can see we have the same kind of structure, and we can then conclude it's just going to be vector AG. Okay, so there's plenty of ways to go ahead to sketch these. Sometimes it's easier to think about the physical interpretation of these and kind of either say, you know what, I kind of want to apply the the parallelogram law, which is what we apply below, or I can just use equal vectors. So here it seems to make sense to either use the parallelogram law of vectors, looks good, or we can use equal vectors. Both of these are valid methods with respect to simplifying these. Okay, last one, let's work in green. We have vector AD, that's going to be one of these, plus vector HG. Okay, so already I see a vector EG here, right? Because I see that vector AD is the same thing as EH, but again, we'll continue for now. Plus a vector HE. Okay, so that means we went from AD down to HE, so the answer looks to be HG, and then we're going to add on an FE. Oh, interesting. And so if you notice here, we can move this vector AD over to the start here. Say we can make the stipulation that vector AD is equal to vector FG. And then what's the situation that we have here? Well, we would then have vector FG plus HG plus HE plus FE. Okay. And if you notice here, we have, and I have to switch to a different color just so it's easier to read. If you notice here, we have vector HG goes in this direction, and then we go back. Similarly, we have vector HE, and then we go back. So meaning we didn't get anywhere. So this is actually just the zero vector in disguise. Okay. And so if you want to as well, you could rearrange these as well. So another way to think about this example would have been, say, we go from H to G. Then we go from, instead of HE, we call it GF. Then we go from F to E. Then we go from, instead of FG, we go from E to H. And the reason why I'm showing you this is that when you use equal vectors to help show what this looks like, you can see here we have some nice harmony. So we end at G, begin at G, end at F, begin at F, end at E, begin at E. This is the same thing as vector HH. And so this is vector 0. So if you have a point that begins, if you're beginning somewhere and then told not to move, then that means you have the 0 vector. And so we saw from earlier we ran into this example up here where if we took vector FH plus vector HF, we actually have the vector FF, which means that you were told to start at F, but then don't move. So hence you made zero progress with respect to a vector. Okay, so you can use the parallelogram law, you can use equal vectors. Typically what ends up happening is you end up having this diagram, what I've shown you, like a lot of sketch marks on it, trying to determine what to do here. Okay, let us continue on. So the book goes into some more detail about the parallelogram law of addition. So this is where we are a bit more formal. So we let vector A and B be any two vectors arranged tail to tail. So maybe I should write vector B in green. So here's vector A, and here's vector B. Then what we do is we want to complete the parallelogram determined by A and B. And so the way to do that is you want to copy, or you could say you want to make copies of A and B. Okay, so here we make another vector A, and here we make another vector B. So we can form this parallelogram. The sum of A and B is the vector with the same tail as A and B, and with its head at the opposite vertex of the parallelogram. So meaning that when we go ahead and complete the parallelogram, we want to start at the tail of A and B and end at the head of A and B. So this was the intuition that we ascribed from earlier with respect to the rectangular prism. And we should say, and place them accordingly. Okay, which you can see from our diagram. Okay. We're going to call, so for example 5, and what the textbook is going to have for us to do, and we're pretty close to done. So this will be the day we're going to finish up early. Or by early, I mean on time. We're going to be drawing vectors. And the textbook just asks you to do this. So it'll say copy each set of vectors and draw vectors u plus v and so forth. And so here I just use some of the support questions to kind of help us, as well as just some of the actual note questions to assist us. So here, let's color code this. So let's call this vector v. And we'll call this one vector u. And it makes sense at this point just to kind of use the diagram they gave us because these vectors are already arranged tail to tail. So that means we want to move a copy of u above. And then we want to create a copy of v to the side. So the resultant vector will be this value, which will be u plus v. Okay? And so this was using the parallelogram method. Parallelogram. If we were to use the triangle method, we would have vector v, and then we would just physically move vector u. And we'd have the resultant vector, v plus u, or u plus v if you prefer. So this would be the triangle method. Okay. For letter B, we have vectors v and u, and they're arranged like this. So let's go ahead and sketch what these look like. For our purposes here, the triangle method looks like it'd be a bit easy, a bit less work. So we'll do that one. So here's vector v. Here is vector u, and they want to do u plus v. Sure. So here we'll take vector u. Oh, that's an A. We want to take vector u, and then we tack on vector v. And so the resulting vector here will be u plus v, like so. Okay. And again, just a little small note, these are not to scale. If you were on a computer, you could probably do these perfectly. You would do these perfectly accurately. But again, I'm not going to use a computer for these because again, my diagram is slightly off. I guess I should have like tilted the V more. But again, I think all of you will forgive me for this. Okay, and then for letter C, we got vectors u plus v. So let's go ahead and just color coordinate these to make it easier. So there's vector u. We'll put this as vector v. So we'll call this vector u. And then this one will be vector v. And if you would like to, in fact, maybe we'll do that for this one. We'll show this the parallelogram method. Oh, we should probably make this a bit steeper. There's vector v. So we want to make a copy of this, copy this above. And it's typical to have the copies as these dotted lines. And we'll have the copy of vector u as well. And the resultant will be the tail of the first between the two vectors to the head of the other two vectors. So this will be vector u plus v. Limitation of doing these things using pen and paper like this is that you end up you draw your vectors so they end up looking very perpendicular. The answer seems to be a horizontal and vertical line, even though that's usually not the case. But again, we do make a note that these are not to scale. You just try to do your best. Okay. Lastly, but not leastly, we have more vector diagrams here. So in the diagram below, A, B, C, D, and C, E, F, G are parallelograms. So we're talking about this is a parallelogram, and then this side one is also a parallelogram. Okay, so that means if you have a look at the sub parallelograms here, FEDH parallelogram, DCGH parallelogram, and ABGH parallelogram. Okay, so what about vector HG plus HD? Okay, so here is HD, here is vector HD. This seems to be the case where we can manufacture some or copy some additional vectors. And we appear to have vector HC. Okay, what about HG plus HA? Right, so here is vector HG, here's vector HA. That appears to be the same thing as HG plus GB. Because we note that vector HA is equal to vector GB. Okay. And we get our answer that the answer to this should be HB. So for these kind of questions, you can either you can use the triangle or parallelogram method combined with equal vectors. And that's like the key thing to make these work. So in example A, I use the parallelogram, and in B, I was using equal vectors. Okay. What about FG? So we're talking about, let's work in green, I suppose. So we're talking about FG plus FE. So what would that be? Right? So take a moment, pause, think about that one. Okay. And so the solution to that one seems as if there should be another point here, right? Because if you notice, it seems like as if there was like another point down here, kind of feels like this should be the case. So could I create like a point I here and say, oh, look, we can just kind of continue on? seems to be the intuition for this one, right? And I would agree that this does seem like that could be something reasonable to do. So if you wanted to, you could call this vector IC. But well, we'll come back to this one in a moment. Okay, letter D here. We've got CD plus HD. Okay, so we've got vector CD plus vector HG. So we started at C, went to D, and then we started at vector H and went to G. So that means we actually have the vector 0. We didn't really get anywhere. And for this last one, we have vector FE plus ED plus DC plus CG plus GA plus AD plus DF. So we want to go ahead and add those all together. So what do we do here? Seems like a lot to sketch, right? And if you notice here, we have ED, DC, CC, GG, AA, DD. We have a nice clear harmony. And so we actually end up with vector FF, which appears to be vector 0. So if I were to draw what this looked like, that means we had vector FE, then ED, then DC, CG, GA, AD, and then DF. We had this kind of structure, but we had just ended up where we started. Okay, so we're going to use a diagram to explain how each vector can be expressed as a single vector. Okay, so here, if we have vector AB, okay, so perhaps I should be a bit more clear with this. So here's vector A, and there's vector B, and then we have a vector CA. So we have some vector, but all we know about CA is that it terminates at point A. And so we can see here, if we're going from C to A and then A to B, then this vector should be vector CB. Because we can see that based on how this diagram had to look, this is what it had. This is the only logical thing it could be. Another way we can arrive at this is if we swap the order, then we have vector CA plus vector AB, which we can then conclude has to be vector CB. Okay, what about vector ST plus vector US plus vector VU? So perhaps we can swap the order of this around. So why don't we write vector VU out front plus vector US in the middle plus vector ST. So it seems like the answer to this should be vector VT. So let's go ahead and sketch what this looks like. So suppose we have vector ST is here. Then we have vector US. So say some vector going like this. And again, these are just arbitrary vectors. And then we have to add on vector, we have vector ST, which is here, vector US, which is here, and then we have vector VU. So we can put another vector here, and we have vector VU. So the resultant vector must be the vector going from U to T. Sorry, V to T. So this is going to be vector VT, which is what we were looking for in our diagram. So the addition of these vectors, again, not too bad. We can go ahead and label these diagrams. And here we showed algebraically why it works, as well as a diagram to help us in the results. Okay, so for now, I think that's a good place to stop. Tomorrow, we're going to look at the subtraction of vectors, and then we're going to have a look at a unit review. So I'll see all of you next time. Goodbye for now.